Hey guys, so today we're going to talk a little bit about hypothesis testing and how we can use it to draw conclusions about an overall population. So, for example, let's say we're given some information about a group of people. On average, an 18-year-old spends 6 hours a day on their phone. And we can conduct a hypothesis test using real-world data to test if this 6 hours a day is a good estimate or not such a good estimate. So we can't go around asking every 18-year-old in the world how many hours a day that they spend on their phone. So we draw a sample. A sample is a small subset of the population. In this case, we ask 20 people who are 18 years old and ask them how many hours a day that they spend on their phone. This data represents that sample. It's just some random numbers that I selected. I didn't actually ask people, and we want to know the average time spent on their phone. So we use this formula to calculate the average, adding up all these numbers and dividing it by 20, which is the number. And we get something pretty close to 6. So we are wondering if 6 is a good estimate. So now we need to see if it differs from our original belief using a one-sample test. A one-sample test is called a one-sample test because we are drawing from one sample. This is our only sample. There's two-sample tests and other stuff that we can get into at a later time, but let's just focus on one sample. So first we need to define our test. So our null hypothesis, H0, is that the observed mean, x bar, which we calculated to be this, is equal to our original belief, mu naught, which was 6. And our alternate hypothesis, let's just say we want to see if the true amount of time a 18-year-old spends on their phone is greater than 6 hours. So that's what this represents, the alternative hypothesis. So our null hypothesis says that there is no difference between the expected mean and the observed mean. And our alternate hypothesis says that we are testing to see if the observed mean is larger than the number that was given to us. And just in general, for alternate hypothesis, we can test whether the observed value is greater than, less than, or not equal to. And if we are using greater than or less than, it is called a one-tailed test since we only care about one side. And if we use not equal to, it's called a two-tailed test because we care about both sides. So now there are two types of one-sample tests. There's a z-test and a t-test. The z-test is easier, but the only difference is that we use a z-test if the population variance is known, and a t-test if the population variance is unknown. And it's more common that we don't know the population variance. So for the sake of it, let's say we do know the population variance, so we can use a z-test. So let's just make up a population variance. So let's say 3 hours is the population variance. So this means that the variation among the data is about 3 hours from the mean. And there's also tests that we can use to test expected versus observed variance, but maybe that could be a later video. And the z-test formula is as follows. The z-score is x bar minus mu naught over sigma over square root of n. Our x we calculated to be 6.735, and our mu naught was given as 6. And our variance, the one that we assumed, is 3. And we take the square root of variance to get sigma, because sigma is the square root of variance, or the standard deviation is the square root of variance, to plug into the formula, and n is the number of observations that we've had. So we plug it in, we get this value. And since we care about going back to our defined hypothesis, we care about if it's greater than the mu naught, we need to subtract by 1. We need to subtract this from 1. Moving on to the t-test, we assume the population variance is unknown, so we need to estimate it using this formula, S, and in R there's a function that you can call to estimate it, but you can also try and plug this formula in if you want to just double check it. But we get this as our population variance, our estimated population variance, and then we can plug it into the t-test formula, which is very similar to the z-test. The only difference is we use S instead of sigma. And we plug it in, we get this number, which is pretty similar to the p-value we got from the z-test. So drawing conclusions, I'm only going to focus on the t-test part since I made up the population variance. So this is our p-value, and a p-value the p stands for probability, and it represents the probability of obtaining our observed mean x bar, given the assumption that our null hypothesis is true. So our null hypothesis is that the observed mean x bar equals the true population mean mu naught. So the probability of obtaining this value, 6.735, is quite small if the actual mean was 6, or mu naught. So the probability is about 3%. And it's a common cutoff to use 0.05% to accept or reject, or you can't accept the null hypothesis, you can fail to reject a null hypothesis, and then you can also reject the null hypothesis. So if the p-value is less than 0.05, we reject the null hypothesis. If it's greater than 0.05, we fail to reject the null hypothesis. In this case, 0.03985 is less than 0.05. Therefore, we reject the null hypothesis, H0, and conclude that the true average screen time for 18-year-olds is greater than 6 hours a day. Thank you for watching, and I hope you have a good day. And I'll link the PDF to this file in the description. Thank you.